particular, when we were talking to him about Jon Snow, said that the really important element of what Jon Snow did was mixing.
Okay, I'm rolling.
Rolling.
Oh.
All right, I'm in a slate.
Mixing the human element.
Predictions.
I'll explain.
Okay.
Okay.
Predictions. Megan Murray.
You look great.
Thank you. Can you see our papers, or we're okay with the papers?
No, papers are okay. Just be mindful to not make wrinkle.
Yeah. Okay.
So
I didn't bring the iPad because it's hard to see in the sun.
No, definitely.
Anyway. Okay, great. So welcome, Megan Murray, to PredictionX. And we were just talking about the course in general, and I'll just explain a little bit more in general. So epidemiology, which you are an expert on, was thought by us when we were planning the course to be a really good bridge between the second part of the course, where we essentially talk about how you go from people just kind of observing the world to trying to make predictive theories about it, to the modern era where there's a big emphasis on data collection and matching up theoretical models and data and having more and more and more data and computational modeling. And so we used the famous story of Jon Snow and the cholera epidemic in London as a way to show that transition. And in that presentation, we talked at one point to Rosalind Stanwell-Smith, who's the head of the Jon Snow Society in London, and we talked mostly about kind of how Jon Snow worked and what the versions of the story that have been kind of sensationalized by people like Tufte are, and what the real versions of the story are. And then we also talked to your colleague from Harvard, Don Goldman, and the things I learned in that, having before approached that map only from this kind of visualization point of view, because I teach data visualization courses, were really about kind of how the methods of data collection that were used were this kind of in the field, on the spot kind of interviews with people, and then looking through records, and then putting the story together later. And the way that that story gets told, it's often like, oh, Jon Snow was walking around in London with a clipboard, and he was writing down, he's making this map as he goes along, and he runs off to the government and says, you have to take the handle off the pump. And that's sort of not true, okay? And it's too bad that it's not true, because it's a great story. But anyway, so that shoe leather epidemiology, as Don called it, that sort of field element. It seems that today, you know, there was this famous Wired magazine cover that said the end of theory, right? And it was all about how everything, if you collect all this data, you can just model the world perfectly without any kinds of theories or ideas. So you asked what the kind of, what we're hoping to get out of this conversation, and it's kind of this tension between people who think that the modern way of doing prediction is using complete data-driven approaches without a lot of human intuition and without a lot of kind of human factors, and admitting that sociology and psychology are really hard to model, harder than things like, you know, diffusion of some kind of infectious agent in water or something like that, where you can use physics. And so I was just going to tell you that on my way here, I was extremely late, as you know, and part of the reason is I got in the car, and Google Maps, which is the ultimate in data-driven prediction that people experience every day, said it was going to take me 35 minutes to get here, and it took nearly an hour and a half, because it kept updating the prediction. And so even we today, in other words, that's part of the emphasis of the course, is that people think about prediction today, and they either think about some weird mystical stuff that most people don't believe, or they think about things like Google Maps or the weather, or you know, stuff that's very data rich, but they just take it for granted, and they take it for granted that it's right. And the course is really about where did all that come from, and what is the human tradition of wanting to know your own future. And you know, so that's why we go all the way back to Mesopotamian sheep entrails and the Oracle of Delphi, and we do talk about astrology and things like that. But so today I will stop talking and instead talk to you. We want to talk about health and people's concern about their own health, but also governments and political organizations concerned about global health and the health of populations. And one of the other things that we've learned talking to a lot of people who think about prediction is that there seems to be a difference between kind of people wanting to know things very personally for themselves and the people wanting to know things on a population basis.
Yeah.
And so I know that you are an expert in tuberculosis. I did not know that some incredible number of people have at least a dormant form of tuberculosis in the world. What is the number?
Well, again, it's one of those things for which there's not great data,
Yeah.
but the number that's tossed around is a third of the world, and I forget how big the world is at any one moment, but is infected with TB. Right. But the vast majority of those people are not going to develop active TB.
Right.
And the important piece is they're not infectious with TB. So.
And so of that third, what, like 10% or something or less is going to get?
Yeah, so again, if you read a textbook, it'll say 5 to 10% of people will develop active tuberculosis within the first couple of years of being infected, and then another maybe 5% sometime during their lifetime.
Right. The really tricky part is knowing which 5 to 10%.
So it turns out that there's enough heterogeneity in those risks that they're not all that meaningful.
Right. And so what I wanted to talk about is there's an element of again, this sort of personal story and like, you know, okay, I'm infected. What do I do in order in the future to avoid getting tuberculosis? Right. And then there's the kind of, you know, insurance company modeling or something like that of, you know, of this group of people, how many people are going to. And so what's the difference in terms of your research now? Are you interested in both what an individual person can do and what a government can do to model and change the future, or are they related, or it doesn't matter?
Well, it's an interesting question. I mean, when we collect data about people's risk factors for a particular disease, and then we wait to see if they get the disease, and then we say this risk factor, this activity is related to a disease.
Right.
That is a population estimate. So not everyone who has that risk factor develops disease. Some people get disease if they don't have that risk factor, and we interpret that population estimate as a personal risk. Right. It's probably not a personal risk, but that's the way that the estimates based on population data are used. So, you know, to the extent that some of those risk factors are quote modifiable, then it becomes something that some individual can do about their own health. So, you know, obviously, if you smoke, you have a higher risk for getting cancer. If you don't smoke, you reduce that risk. So those are modifiable risk factors. But a lot of the risk factors for disease are not modifiable. Right. They're either genetic or the sort of the more tricky ones are things that are associated with someone's social economic status. So sure, if one was wealthy, one could change their risk, but since they're not, they can't change their risk. And so I think there's this place where we think of risk factors as modifiable, and that's actually even harmful in some senses because it would kind of shift the blame for disease to the individual.
Right, and it's almost like there's some diseases where, if you take the snow cholera story, for example, there's a relatively easy fix. In other words, you cannot have polluted water.
There is, except you know, if you take away access to water, then people also don't have water.
Right. Assuming that there's a water supply, then having the water supply not be infected is a relatively easy thing to do. But
not really.
Not really? Even
so
that?
I mean, sure. There was I think what happened after that is that for a period when they finally kind of believed the data, they asked people to boil their water.
Right.
I mean, people don't boil their water because it's time consuming. You need fuel. Actually in that period, I imagine that fuel wasn't cheap. But if you're really thinking about having a clean water supply, it's a massive undertaking in a place that doesn't have a clean water supply. It means developing sanitation, developing sewer systems.
I think what I meant was that there, in my naive view, and so maybe I'm still wrong, but that there are some diseases where there's one very obvious cause, and in other cases, you know, there's genetic disposition, and there's, you know, transmission methods that you can't control, and there's all kinds of.
Well, so the weird thing about infectious diseases is there's always a cause, right? There's a cause there's some organism, bacteria, virus, you know, parasite that causes it, but if we just it's a kind of a limited way of looking at it,
Right.
because there's a reason why that pathogen is that one is exposed to that pathogen. You know,
And that actually sort of is the point, is that
Yeah.
a lot of people think that once you figure out the cause, you're kind of done. You just sort of fix that. And that is very not true, as we know from our own experience and from studying this. And so can we talk for a minute about the approaches in your field that people take and kind of putting them on some kind of spectrum, from much more, field and experience, human focused, to I've never met a patient with this disease and I'm looking purely at data.
Sure.
Not that one is good and one is bad, okay, but just,
Well,
what are people working on now?
I think
The airplane a chance to pass.
sure.
That's really loud.
Wow, that is, yeah. Sorry about this situation. Is it okay otherwise?
Oh yeah, it looks great.
Okay, good.
How's the light? Is it starting to hit the back?
No, that's okay.
And this,
Can you hear both with the shotgun? Can you hear both of them?
by the way,
No,
The
it's
wind
not.
has been
A little noisy. You want to adjust?
Yep.
oops.
1 second. It looks beautiful though.
Well, I forgot to put my sunglasses on and I'm squinting. Do you care? Do you want me to put the sunglasses on or no?
Too squinty. Is it still
You know?
pretty bright even with this?
It is, but that's okay.
I'm thinking maybe I can use the scarf as a bit of a shield because we don't
Sure.
Okay, there's a
It's like a-
thread there.
a bit of a windshield.
You wouldn't believe, I'm not usually very vain, but like this
Sure.
HD video is terrible, and if there's like a thread on your scarf, people will go,
Yeah. You can't just blur that.
Because we don't have the shields to put it underneath, but
Okay.
is that all right?
yes.
Just go that way a few inches. I just see it starting to hit the back of Melissa just a little bit.
Oh,
Yes,
God.
This one gets more to the top of the.
You want me to move? Is that easier?
Got it? Nope. I don't want you to think that's good.
Okay.
Just need a little adjustment. Cool. All right.
All right, you guys good? Just wait till she sits down. Okay, so if you remember, the question was about the numerical versus other. Okay, great. We're good?
Yep, you are good to go.
So at one extreme, there's what you're calling shoe leather epidemiology, and it's still, of course, practice. So the Center for Disease Control have a whole army of, and the Epidemic Intelligence Agency, I'm actually probably getting the name wrong, but who respond to outbreaks. So they're called in, and if there's a bunch of cases of diarrhea in some town, and to see if they can figure out what the cause is. And sort of the classic story is, someone had a church picnic and served undercooked chicken, and half the town got salmonella, and the CDC comes, finds that out by asking everybody questions, and figuring out which actual food thing at this picnic was the cause of it.
Mm-hmm.
And that happens whenever someone, whenever the public health system is well organized enough to identify an outbreak and then ask for someone to come and deal with it. And the other extreme, there's infectious disease modeling, which is mostly computational and has gotten very sophisticated in the past, say, decade or more. And that usually uses parameters or estimates around what we think the quantitative aspects of the natural history of the disease are from the literature, and meaning from previous studies. And those get inputted into a model that can range from relatively simple, say a deterministic differential equation model, to a super complex model where every single agent in a population is individually modeled. Those can be very useful if they're looking at population processes.
Yeah, we're going to have, in the course, we've done a bit of research about online tools for looking at those kind of models. And so, there's the SER models, the SEIR models, and then these agent-based models. And so when you say differential equation-based ones, you mean the SER and the SEIR models?
Yes.
And then the agent agent-based ones are where every little thing about. Now, what I don't understand is the SER and the SEIR are clearly about a population. That's not
Right.
about an individual person. So are the agent-based ones meant to apply to an individual person, or they're meant to model the behavior of individuals or the effect on individuals and then look at the whole population?
They're meant to capture exactly, at least when they're used for infectious disease epidemiology, exactly the same things that the differential equation models are meant to capture, which is population dynamics. So, you know, when will an outbreak peak? How many people will be infected at the end of an epidemic? Will there be cycles? Will it recur? At what frequency will it recur?
Got it.
The difference is that the SEIR, or whatever you want to call them, SIR models, are fairly simplistic, and we're assuming that the entire population is acting in the same way.
Right.
So one can introduce a little bit of variance. One can say, okay, some of the population is has this genetic trait, and some of the population doesn't, so they're at lower risk than another group.
Right.
Or one could add, say, a risk factor for TB. Whether one has HIV or not is a big factor in whether one's going to go on to develop active tuberculosis. So one could add HIV to that model. But if you want to add lots of things, HIV and other diseases and other risk factors, it gets really messy, and then people turn to these agent-based models.
And is there in other areas of life science, and so things that are really genetically focused, for example, I know that there's a lot of people who are basically just biostatisticians who themselves are not experts on the science. And then in my own field, in astrophysics, we don't have astrostatisticians too much. We want them, and actually I have trained some who have become that, but that's sort of a new thing, that somebody would give up on their own science and do just the math part. And so I'm kind of curious, in epidemiology, are there people who you know, sort of only go in the field and then collaborate with people who do the statistics, or single people kind of in the John Snow tradition, you know, going across all of those areas, or is it a mixture?
I think it's probably more the former, that I think at this point, especially in something like genetics where the statistics are pretty complex, the question of what's an interesting genetic question. So what do we care about when we're looking at particular diseases and whether they have genetic risk factors is not something that is part of the training in statistical genetics.
Right.
I mean, I'm sure people would contest that.
No, but I mean, this is what's happening. I think it's important to point out in the course, because in the course, this is a lot of people looking at this who've never really thought about these things before, and this kind of specialization within specializations is something, particularly a lot of high school and college students look at these online courses, and if they want to know, like, if I have a career as an epidemiology or an epidemiologist or a statistician, you know, what does that involve, and who might I be working with, and, you know, how far outside of what I learned in school does that go?
So, I mean, I think there are statisticians. There's a whole department of biostatistics at the School of Public Health right next door, but who don't have a substantive area, so they don't specialize in a particular disease. Right. And then there's lots of epidemiologists and physicians who actually aren't necessarily trained in epidemiology, who have scientific questions, and there's a lot of very valuable collaborations between those people. But there still are also people who do both, usually as part of a team, or as maybe the leader of a team. And some people are actually, you know, it's one of the most sophisticated statistical geneticists I know is also a physician and practices rheumatology. Yeah, and I think that those kind of large collaborations are important in science today in ways that they were not so important 100 years ago, or even 25 years ago in some cases. And I just was going to say that we like to try to tie different pieces of the modern simulations together in terms of the approaches. And so just for your own information, I should tell you that in astrophysics, I work on star formation and how new stars form out of gas in the interstellar medium. And the most simplistic models basically just have gravity and a little thermodynamics, if that, in them. And then when you get more
more sophisticated, you have to add things like magnetic fields and ionization and chemistry. And then the real problem is we don't have any such thing as an agent-based model. Whereas we don't have things that get really specific, that can add in things like, you know, the geometry of some particular region, which would be equivalent to geography in what happens in epidemiology. So,
well, but is it really, when you say it's a real problem, is it sometimes we add detail that doesn't actually improve.
Oh, no. That is absolutely true. And my own work concerns how much detail has to be added before we make, and that's interesting, I should ask you about that. In our world, we make what's called synthetic observations of the simulation. So the simulations are these very idealized things that we can't actually observe. And I never thought about this, but you have the same kind of problem. In other words, you can only go to Peru, say, and talk to people who have tuberculosis, who have been exposed, I don't know, some certain number of times a year, and you can only talk to certain numbers of people. And is that kind of sampling, that kind of observational bias of what you're getting, included in the predictive models, or do you assume that you just have a random sample and that's enough?
Well, it's not included in the model, but it's included in parameter estimation.
Okay.
So, you know, if there's a bias from the way that sampling is done, then that's a flaw of a study, and either one wouldn't believe the results of the study, or we wouldn't try to come up with a way of compensating for some kind of bias that had been introduced that way. I think what's, you know, from the infectious disease perspective, what is unobservable is what the effect of a particular change or intervention is going to have on a long-term basis. So we talk about, you know, we can do a vaccine trial and say this vaccine works, because if you take people who are vaccinated, they don't get disease as often as people who weren't vaccinated. But what we can't predict from looking at study results is, okay, let's say we vaccinate a whole population at a particular age and with a particular set of risk factors that will make the transmission of that disease happen at a particular rate. What's going to happen in over time? And so those are, we can observe it 20 years from now, but then it'll be too late. So that's where modeling is actually kind of useful, where we think we can sort of look at how many interventions do you need to, say, control cholera. Is a vaccination program going to be enough? Do we also need a water program? Do we need both? Do we need more than that? Since we can't do that study, that would be permutations after permutations, we can model it.
Experimentally, just sort of have a simulation of that. But then my question is, we have this story that we tell in the middle of the course. It's called The Path to Newton. And we go from Babylonians just sort of looking up at the sky and noticing that there are patterns and that they change, and then making very accurate records of it. And then you go, thousands of years pass and people go into more and more detail, making these observations, and then making models, mathematical models like Kepler, of how orbits work and how that's consistent with the patterns you see on the sky. But it's not until you get to Isaac Newton where he says, I understand, this is all caused by gravity. There's this magic force and it works like this, and now I can make predictions without any prior data. And a lot of people, including people in medical sciences, say, we don't have theories like that. In other words, we don't have a theory of gravity where you can kind of a priori say what's going to happen. And so my question is, in those modeling exercises, how much of it is looking at what happened in the past and the efficacy of what happened in the past, versus people actually having theories, maybe based on genetics or something like that, that are input into the model systems without having equivalent things have happened in the past?
So it's a...
Whoa! Okay. You guys okay? Keep going?
Hold on.
Wait. Okay.
This is like 40 mile an hour wind.
Yeah, this is...
It looks like a sail, by the way. It's not meant to be.
I know. I know.
It's stable.
Wow.
Drew, you've had to do all kinds of jobs in this course, but this one is probably new. Did the scarf work or no? The scarf did work?
Yeah, it's great.
Okay, well, I'll let you know where I got the scarf, and you can get a whole supply of them for other people.
Yeah.
Yeah.
It's perfect.
What's it working to do?
Yeah.
It's just blocking the wind.
Oh, I see.
This?
No, her scarf.
Oh, her scarf.
Because it's so thin, doesn't like hit against it, it just protects.
Here's your slide.
Yeah.
I'll hold this. Alyssa, do you mind
we
just
can,
moving in like maybe an inch or two? Just
no problem, but I don't want to
back.
pull anything out. I can safely move an inch.
Yes.
Okay. Is that good?
That's good. That's good.
Okay.
Just get the sun off your back a little bit. So you,
I
you
can
might,
also.
You might want to check here.
Yeah, I will. I mean, for the most part, it's pretty locked down. I've hardly moved the camera at all.
Let me just look at my questions and.
Yeah, me too.
Okay, I have like 3 more things I want to ask you, so I think we'll be okay. We okay so far, Drew?
Am I okay?
No, I mean like substance-wise.
Yeah.
Okay. I'm sorry that you're standing there holding a thing, and I'm sorry that I was 12 minutes late.
So theory, right? Or
Yes.
or,
Yeah. Okay. Right. It's sort of how much of it is empirical and how much of it is theoretical from a kind of first principles.
Right. Well, so you know, in biology, there aren't big theories the way that, you know, gravity is a big theory in physics, but there are lots of little theories.
Mm-hmm.
I mean, we have, you know, our understanding of how we think cells work and how, you know, metabolism works, and you know, I think it's a dialectic between one having a hypothesis or a theory,
Mm-hmm.
and then going back and seeing if the empirical data supports it. It's far more driven by observation and empirical, you know, I hesitate to say data because a lot of it's driven by impressions that people have, but increasingly it's driven by data. But without having some idea of what one thinks that data means, I'm not sure that we would be making the kind of, you know, that we'd get to a real scientific answer to a question. So, you know, yes, we could observe that here's a constellation of things that are associated with the development of a disease.
Right.
But there's many routes through which that could work. So, you know, an example we brought up before is poverty. You know, poverty. We could say poverty causes TB. Okay, so that's kind of obvious, but it's not all that useful because there's probably many ways in which poverty affects particular biological determinants that then lead to TB.
Right.
So I do think people have more theories than they realize. It's not entirely empirically driven, and that's probably a good thing. Most of them, or many of them, are then falsified, and we move on to the next ones.
And so one general question that I wanted to ask you was, again, Don Goldman brought up that he's not sure if John Snow should really be seen as the father of epidemiology, given that his techniques in terms of study design were not, I don't know, very good according to modern standards and systems. And so, you know, people have brought up case-controlled studies and longitudinal studies and cohort studies, and there's this whole story I read about a hierarchy of evidence and what's allowed and what's not. And so, can you, if you were going to criticize John Snow for his study design, where he looked, you know, I said to Don, you know, Don said, well, he only looked at the sick patients, you know, there was no control. And I said, well, what about, you know, the rest of London that didn't get sick? And he said, no, that's a poor study design. And so what is it that you would say in general has completely changed or not changed in the last 150 years about the way people do these kind of studies?
Well, I'm going to be a dissenter here.
Okay, good.
I like to judge things by whether they work.
Okay, good.
And so John Snow, obviously, it worked.
Yeah.
He took his handle off, or got somebody to take the handle off, and it was effective. I think we can often be, you know, this. One of the problems with the way the complexity of these fields, you know, has just kind of skyrocketed, so that we have statisticians and we have study designs. It's really important to think through where biases occur in data or data interpretation because of the way data was collected. But I think we can do that outside of a completely regimented sort of set of these are good methods and these are poor methods. And I think it's a challenge that is, you know, in many types of science, we've gotten overly regimented as to
I'm
what's
smiling because I agree
acceptable,
with you. The same is true in my kind of science.
Yeah, I mean, you know, we don't accept that you can just ask people, you know, like, well, what do you think happened? Why do you have this? You know, that doesn't count as data somehow. It has to be, you know, quantitative, and we know that doesn't always make sense. And so I think we have to use all the tools available to us, and we have to continue to think.
Yeah, I think this
you
is a
know.
dangerous thing to say, but I'm going to say it anyway. Part of the inspiration for this course was the economic collapse caused by the quants in 2007, 2008.
Yeah.
And that was a classic case of, people just taking models and data, and then the people who were supposed to make decisions based on them, the bankers, did not understand what was going on, and the people doing the modeling didn't have the experience in banking to mix
Right.
into the mathematical modeling. And so, yes, that was a disastrous outcome in that particular example.
Yeah, and there's always going to be enough complexity that that story sounds like, well, if they just had kind of talked more, if we put a Band-Aid on a few things, it would all work out. But
Yeah.
I'm not sure that we can ever really get at all the complexity in human behavior without just reproducing the entire world. So,
That's been done in several movies.
Yeah.
Anyway, but
Yeah.
no. I think that human behavior piece of it has been acknowledged in many fields. So we will talk about finance in the course, and you probably know that behavioral economics has gotten very popular recently, and that goes against things like basic game theory, where you say everyone just acts in their own self-interest by some magical principle. And so people have admitted that they need to model human behavior a little bit more. Okay. So the other question I wanted to ask you before we go is just about this. Oh, okay, sure. Here, I'll show you this so that.
I need to know.
By the way, your talk was great. I learned a lot. If I could ask you all about tuberculosis, I would, but we don't have time.
For the white shot?
I'm just trying to do a different lens on the camera.
Okay, I just,
Take me 30
she's got another question, and then we want to do that, so.
We'll just need like
3 minutes?
Or
Okay.
two would be good. We'll just throw that out of the way and switch the lens.
We just need a minute for this just to pop out the other side.
Okay.
It looks really bad when it goes by.
9:51.
Oh.
So it says
9:51?
Yeah, I don't think the wide's gonna work. I think we have to cut the wide. Unless, do you think
Well,
it's
I think
I don't
Jared's
really know what they're
Jared's
talking
gonna
about.
need the
It's
wide.
really important, and this question is very, very important because we need this wide.
This is only going to take like 2 minutes.
And he needs to take 2 minutes. But we gotta wait.
Just because Jared's really going to need the wide shot, because whenever the sun goes behind the clouds,
Right.
the shot changes so drastically.
Okay.
So we'll need that shot.
It only happened a few times. So.
Yeah, but that's nice to have that shot of the sun shining, so there won't be.
Do you guys need us in whatever this wide
Yes,
shot
we
is?
do.
Oh, okay.
It'll be really quick though. It'll be
Okay.
like a
Cut to nothingness
40
while you're talking.
40-second
Yeah.
shot.
Sure.
Okay, got it. Okay.
I think it's coming back.
Yeah, okay, we're good.
Alright. Quick
Good.
question.
Great.
Okay, my quick question. Go ahead. Okay, so just to tie this together in a weird way to Jon Snow. So Jon Snow made this very famous map.
Yeah.
And I personally am very interested in data visualization. And so I'm curious about diagrams like this one, which the title of this, which is a slide you showed in a talk recently, says an atlas of genetic correlations across human diseases and traits. And so people use these kind of visualizations now to build into modeling diseases. And can you just tell us in a minute or so roughly what this is? And then we'll have a write-up on the website accompanying a diagram like this. So.
Well, this is a paper that I had nothing to do with. I was just showing as an example, but it's showing the statistical correlation between genetic groups of genes that have been associated with a particular disease. So the question is, if we think, as we speculate, that perhaps some kinds of metabolic traits put people at risk for TB, then we might ask, okay, so does that mean that particular metabolic diseases, diabetes for example, is correlated with TB? And it is. But you can go further and say, okay, so is that due to environment or is it due to genetics? And so one could then ask, is a set of genes that's associated with diabetes also associated with TB?
Mm-hmm.
And this particular study did this across this huge list of diseases, looking at sets of genes that have been associated with those diseases and seeing how much they were correlated.
I'm glad I asked, because our next interview about this topic is with George Church.
Oh, great.
Who, of course, is very interested in exactly this
Yeah,
kind of thing.
yeah.
And so
And-
we will connect this through to that interview. And I might ask you some more questions by email, just so that we can make...
and I'd love to hear more about it. I mean, I am one of those people who actually doesn't understand visualization.
Oh, okay.
I never know how to present data, so
well,
that other people do understand it,
I
you
will
know.
return this favor, if you wish, with a coffee about
Yeah.
visualization. I actually
Yeah.
gave a talk at the Society for Epidemiological Research when
Oh,
they had the
great.
meeting in Boston
Yeah.
at their request, saying that epidemiologists don't know how to do data visualization.
Well, I think we don't, but you know, I think that some people are just programmed in a way that we're not particularly visual. So we.
I
you
thought
know,
your slides were not bad, so you know, it's fine.
Great.
But anyway, so do you want me to do the thing where Megan introduces herself really
no,
quick?
what we need to do is get a white chart.
Okay.
So don't worry about the introduction.
So you're
We have a lower third. Yeah.
you're
So-